There will be two presentations. First, I will tell you what kinds of magnetic simulations are available with QuickField and what parts of package may be applicable for this. And then my colleague Sergey Yonin will explain in more details how to perform simulations of systems with permanent magnets. So QuickField is a multidisciplinary package with plenty of possibilities for field simulations. It includes magnetic problems, electric problems, and thermal and structural problems. QuickField is multi-physical package, and all the parts of the analysis may be combined. So it is possible to couple results of one problem to other problem. And specifically about magnetic simulations, it's very important to know what it is possible to calculate magnetic forces in magnetic part and then bring them to stress analysis and understand deformations, stresses which are caused by magnetic forces. Stages of solution in QuickField in magnetic simulations are absolutely the same as in any other part of QuickField. You should define new geometry, specify problem parameters, and get your results. What is specific to magnetic simulations is parameters. Let me speak a little bit about, let me explain a little bit how we define magnetic parameters. QuickField allows to define dependency of inductance over H in two ways. It may be in linear problems you may define permeability, or in nonlinear problems you may specify the curve. BH curve may be specified. So we use first or second quadrant of BH plot, and if there is no permanent magnet in the system, permeability may be specified as table of B and H values. On this example, you see some strange material because it is not physical values entered. But generally, it's very easy to define the curve. You may bring the table from Excel, you may enter them point by point, and then these parameters will be recorded and displayed in QuickField model editor, curve editor and used in the solver. We use splines to smooth the table, so in many practical cases it's easier and better to use less number of nodes to enter, to have more smooth representation of the BH curve. If you have permanent magnet, it is specified by coercive force. Coercive force in our terms is shift of the curve left from the zero position. After you specify coercive force, your curve will be moved to negative values of H, and the same procedure will allow you to specify the table of pairs of BH values to find the curve. This checkbox, if it is switched on, you will specify the curve. If it is switched off, you will specify just one value of mu, which is tangent of the decline of the curve. From three formulations of magnetic analysis in QuickField, you may specify permanent magnets in two of them, in magnetostatics or in transient magnetics. AC magnetic formulation supposes that all parameters change with time as sign as harmonic functions. So any permanent magnet is a constant, so it cannot be specified in AC magnetics. But in magnetostatics or transient magnetics, you may specify magnets using block properties or as it will be shown later in the Sergei's presentation, you may specify it by boundary conditions in some cases. But generally speaking, there are two problem formulations in QuickField, magnetostatics and transient magnetics, which allow permanent magnets. And you should also understand what results of magnetic simulations, forces may be brought to mechanical analysis as a couplet source, and then you may calculate the magnetic stresses, deformations, using the magnetic forces. Now, Sergei will explain in more detail basic principles of using permanent magnets in the QuickField problems.
Hello dear colleagues, thank you Vladimir. My name is Sergei. I'm a QuickField support engineer. Let's start our event. Today I'm gonna offer you 6 problems. First problem is a single magnet problem. It's the easiest one. Second problem is a two magnets interaction problem. Third problem is about the magnet and ferromagnetic interaction. Fourth problem is a problem of magnet and direct current interaction. Fifth problem is about the magnet and transient current. And the last problem is about the automation of calculations. Let's start from the cylindrical magnet example. It's made of neodymium iron boron alloy. Thickness and diameter of a cylinder, that's the values. Coercive force and the remanent flux density are known. Let's solve the problem from scratch. We run QuickField, create a new problem with the name magnet. Problem type is magnetostatics. Module class is axisymmetric. Length units millimeters. And I finish. Sorry. Well, and now I should draw the geometry. I'd like to add vertices and to link them. First vertex, second, third, and fourth. Let's zoom it. Let's link the vertices. So, the upper part of a cylindrical magnet cross-section is ready. Now, I should draw the air. It's a half of arc. Now the drawing is ready. Now let's label the geometrical objects. This is the magnet. Sorry. That's a magnet. That's how I label it. That's air. And that's an external boundary. Let's give properties to our objects. It's a magnetic statics problem, and I should set permeability or coercive force. Also, I can set currents or current densities. In case of air, I should just set relative permeability equals to 1, and I press OK. What about the magnet? At first, we set coercive force of a magnet. That's a value. And also, we set remanent flux density. So we obtained the demagnetization curve of a magnet. Note that permeability is calculated automatically, since the magnetic properties are linear. And I press OK. On the external boundary, I should set magnetic potential. This value equals to 0 because magnetic field drops to 0 on the external boundary. Now I build the mesh and solve the problem. Our aim was to calculate magnetic field distribution along the axis. To do this, we should select the contour and display x-y plot along the contour. I select the axis and click on x-y plot. That's a magnetic flux distribution along the contour. Also, we can show field values as table. I click here. I can adjust this table. Let's view just the coordinate and the flux density component. That's an adjusted table. Now, the magnetic field density lines are rather coarse, and the solution isn't accurate enough. Look at this. Very coarse one. If we refine it, we'll get better accuracy. I click on Solve and Refine, press OK button. You can see that the mesh step was refined, and that's the refined solution. Now I select the same contour and display field values table. Since I'm going to show you another way of the property settings to compare the results, I'll copy the table. The values will be stored here. Okay. Let's see the color map and display the errors of magnetic flux density. Field picture properties, factors of flux density, and the color map. That's color map. That's a legend. Let's take a look what we can calculate here. We can display local field values. First, I should clear out the contour. I press here. Now I can calculate field values in the arbitrary point of the model. Here I can obtain flux density, magnetic field strength, permeability, energy density. How about the magnet? Note that permeability is not equal to 1. Okay. Also, we can calculate integral parameters, such as magnetic flux density. Magnetic flux. That's the value of the magnetic flux passing through the cross section of a magnet. Another way of a property settings is the following. Accept the cursive force of a magnet, we label upper edge of the magnet. We label it and set the property of a tangential magnetic field. The value is the same as for the cursive force. Then we should remove the cursive force value from the magnet block properties. Let's remove it. 0. And let's solve the problem. That's the same magnetic field picture. And let's do the same calculations as in the previous problem. Not a problem, but settings. Add view table, adjust the table, and let's compare the results with the results from the previous settings. For example, for 2.5 millimeters, values are the same. Also, they're the same for any other point on the axis of the magnet. Permanent magnets never work separately. They create a field or force in the system. Let's calculate the force of two cylindrical magnets interaction. I will use previous problem. To get another magnet, we can copy the previous and set the distance between them for 5 millimeters. Let's do it. Right-click, duplicate selection, displacement, that's a copy of a magnet. The distance between the magnet is 5 millimeters. To get attraction of the magnets, we should set the same direction of a cursive force for each magnet. Let's do it. This magnet is labeled. Let's label another, but it's not one block, but it's another block. Let's copy permeability value. Note that the direction of the coercive force of the magnets is the same. Now it's 0. It means that the coercive force directed to the right. It's 0 for both of the magnets. Also, we should remove the label of the tangential field. Okay. Let's build the mesh. The mesh is good enough. And solve the problem. That's magnetic field picture. We're interested in the force acting on the magnets. Let's calculate the force acting on the left magnet first. I select the magnet. And then I calculate mechanical force. It's 11.335 Newton. The direction is 0 degrees, so that this force is directed to the right. It's the force of attraction. Let's calculate the force for the right magnet. It's 11.316 newtons. And this force directed to the left. Its horizontal component is negative. Means that it's directed to the left. You may note that the values differ a little bit. But we can get better accuracy if we refine the mesh. Let's do it. It's 11.23 for the left magnet. And 11.259. Well, it's better. If we refine the mesh again, we can get even better results. Now we may easily solve the problem for the magnets repelling. We should just change the coercive force and direction for one of the magnets. For example, for the left magnet. I change direction. I write 180 degrees. Press OK. can see that the magnetic field picture changed visibly. They denote to repelling. Let's zoom the picture and calculate repelling force. Now it should be directed to the left. That is, horizontal value is negative. The most practical example is the following. Permanent magnet attraction to the steel, as everybody saw. Let's change one of the magnet's properties for the steel with relative permeability of 1000. For example, I'd like to select this magnet. No. So I have another block label. I enter new permeability for this block. Press OK. This label will be unused and we can remove it. Let's solve the problem. It's another magnetic field picture. Let's calculate the force. That's mechanical force directed to the right. It's a force of attraction. By the way, what if we change the coercive force direction on 180 degrees? Let's check it. Let's press 0. Solve this problem. Nothing changed. It still remains towards the magnet. No, not the magnet, but the steel cylinder. Go again. Now let's consider a system with a permanent magnet and a source. For example, we selected a loudspeaker. Its coil with the current oscillates in the magnetic field of a permanent magnet, so that the oscillations transfer to the diaphragm attached to the coil. Let's solve simplified version with direct current in the coil. The problem type is magnetostatics and replaces axisymmetric, and it's called speaker. That's a geometry. External boundary with the A equals to 0 property. Also, we have the blocks. That's an air. Of course, permeability equals to 0. Oh, sorry, equals to 1. That's a coil. We set total amp turns for the field source. That's a magnet with the magnitude of coercive force. And that's a frame. You can see that its magnetic properties are nonlinear. Let's view field picture. Our aim is to calculate the force acting on the coil. It's a force directed to the left, as you can see from the direction and sign of the horizontal component. By the way, we could be interested in calculation of the coil inductance. Inductance is a ratio between the magnetic flux and the current. That's formula. Inductance depends on geometry and the medium magnetic properties. So we should take the frame situation into account, conditioned by the permanent magnets. I'm going to show you color map of flux density. As you can see, the values are pretty big. And also, I'm going to show you the permeability color map. As you can see, the values are different in the different parts of the frame. Means that the frame is saturated. That's a 531. That's a 797. So they differ from one another. It means that we can't just exclude the magnet, because to calculate the self-inductance of a coil, we should take into account only the coil magnetic field. To calculate the inductance, we will use advanced technique of magnetic state input, which is possible to couple to magnetic problem. In the first problem, we calculated the media state, the magnetic permeability. Then, we transfer the magnetic state to the second problem. And in the second problem, we will calculate magnetic flux induced by the coil. Here's the second problem. There, as I said before, there are no sources except the coil. Let's check it. Gaussian force of the magnet equals to 0, while the field source is the coil. The total ampere turns for the coil remains the same as for the previous problem. And I want to show you how to make a data link. And the problem properties, I press on button links, and here we can see a data link for the magnetic state. That's here. Let's take a look at the solution. Now we may calculate it again. That's a magnetic field picture. Let's show color map. Now the magnetic field is very weak to compare with the previous example, or previous problem. But as for the permeability color map, that's the same. Now we can calculate the inductance of the coil using stored magnetic field energy approach. I selected coil. No, I shouldn't select the coil. For convenience, we may use an inductance wizard. I can use one of the approaches. I'd like to use stored energy approach. We calculate the stored energy. We select the source, and the calculation is ready. That's the value of inductance. We display it here. Actually, the coil current is an alternating one, and we can simulate it. It's a system with a parent magnet and the source of an aperture signal. It's a transient magnetics problem. For example, we may connect the loudspeaker from the previous problem to the meander voltage source. Meander voltage source is a rectangular shaped periodical signal. This task is realized by the embedded circuit editor of QuickField. That's geometry. That's almost the same as for the previous problem. But the problem type is the transient magnetics problem. Other class is still axisymmetric. And also, we have another file. It's a speaker QCR. It means that we have a circuit in this problem. Note that we should set the conductivity for transient analysis. That's conductivity of a coil means that coil is made of copper. We have the properties for the frame. Now they are linear. We have the magnet with the same coercive force. We have the same edge labels on the external boundary. And also we have a circuit. That's a source. The rectangular shaped voltage is set using signal function. The argument of a signal function is sinus. That's elements of a circuit. It's a coil. It's taken from the geometrical objects, and it's a capacitor. It doesn't present it in the geometry. Our aim is to view time plot for the force acting on the coil. Let's do it. That's a window of the post-processor. That's time plot. Here we could set some of XY plots, sample flux density, but it doesn't matter now. We're interested in the force calculations. I add curve of mechanical force. And that's a horizontal component colored with red. Also, we can display the results in the circuit post-processing. We can view input current and the voltage on the elements. That's a voltage on the coil. That's an input voltage. And that's capacitor voltage. And the last problem of our webinar is about the automation of calculations. Let's take two prismatic permanent magnets and study dependence of the force from the air gap between the magnets. We can do it manually, but it's a very time-consuming task. In the QuickField, this problem could be eased using utility label mover. That's a plain parallel problem, and I should just adjust it a little bit. I'd like to show you how the axisymmetric problem differs from the plain parallel. Let's do it together. Now, I don't know whether I have local levels. Yeah. Let's give level properties for the right magnet. This magnet will be attract Okay. Let's solve this plane parallel magnetics problem. That's magnetic field picture. These magnets are attracted. You can see that the horizontal component is much more than the vertical one. And now let's start serial analysis. I press on ferromagnetic analysis with label more button. Select serial analysis and add values. I add value of mechanical force. I mean that it's horizontal component, and I add it. Now I should record steps. I'd like to move the block magnet, which is a left magnet, and I'm going to displace it on 1 millimeter. It means that I will displace it to the right, and I add this step. Let's repeat step while possible, and now we can get results. Now QuickField generates problems and solves them. You can see it on the background. That's not very good. That's the last problem. You can see that the magnets are as close to one another as possible, and the mechanical force now is maximum. And that's a plot of the results. It's a dependence of mechanical force from the step or the distance between the magnets. It was the last problem of our webinar. For more information, you can go to our website, QuickField.com. Thank you for attention. I hope you enjoy our next webinar. Goodbye.